So before we start the video, I'm going to give out my kudos, my appreciation to this guy right here. This is an energy drink, 200 milligrams straight to the brain of caffeine. And this single-handedly helped me get through my first series of O-Chem. We got this. We got this. So if you guys are here right now, that means you guys are either reviewing or starting your O-Chem series. And from what I've heard from other students, that again, it's O-Chem starting out isn't too bad, and then it gets really bad, and then it's not too bad. I finished the first half last year, so I'm a student as well, and I'm going into my second half, my second series of O-Chem, so I'll let you guys know how that is. But I remember when I first started O-Chem, it was incredibly daunting. It was a little bit scary. I was a little bit nervous going into it, but I promise you it's not as bad as it seems. Once you guys get into a habit of practicing and just continuously doing practice problems, I promise you, you guys will get the hang of it. And it turned out to be super fun. It's something that I enjoyed. There was obviously some moments where, you're going to be up a little bit late, cramming, trying to get everything down. But I promise you, it's not as bad as it seems. So let's get into it. I know you guys are eager to start. You guys are studying. So let's get into it. So this is what we're going to be doing this video. Just kind of a background about what we're going to be doing. I like to structure these videos based off of practice problems. Something that helped me get a really good grasp of the content in O-Chem for my first series. We have O-Chem 31, 32, and 33 is how my school works. So 31 is what we're going to be doing. Is just doing a lot of practice problems. And a lot of the videos out there were super helpful for me to understand O-Chem. And the certain topics that we were learning, but the practice problems were never challenging enough, or there was never enough volume to do these practice problems. And obviously office hours are not open at 12 or 1 p.m. or 1 a.m. sorry. And so I kind of had to struggle through it. And so I hope this video is helpful for you guys, a student teaching other students. So in this video, we're going to be doing a little bit of a review of Gen Chem. So right here, we'll be doing a little bit of a review of that. We'll go into the basics of O-Chem. I'm sure you guys have seen things that look like this, or something that looks like this. And that may seem a little weird, but I promise you, using your prior knowledge of Gen Chem, it's super easy to get a hang around. And we'll have a lot of practice on that as well. And then we'll go through formal charge, hybridization, dipoles, geometry, a little bit of functional groups work, and resonance and curved arrows. So all of this should be a review for you guys. I'm not sure how your school teaches Gen Chem. And if it's not review, or you're kind of rusty on it, no worries. We're going to be going over it anyways, because it's important to have a decent understanding of Gen Chem before we get into O-Chem. So that's what we'll be doing here as well. And then these guys, that's going to be O-Chem for today, and this will be O-Chem as well. So mostly review, and a lot of the O-Chem that we're going to be doing is going to be using past knowledge of Gen Chem, so a lot of the review stuff and incorporating it. So let's get into it. So like I mentioned, we're going to be doing review first. So this is going to be some Lewis dot structures. This is really important because understanding how to draw your Lewis dot structure will help you to transform it into what we call bond line structures, which are stuff that looks like this. And I know that looks like a lot of gibberish right now, or it may, unless you kind of have already a little bit of an understanding of what it is, but we'll go over that later. So let's start off with this guy over here. So OCS. Before I start, let me make sure this is something you guys can see. There we go. So before I start these types of problems, I like to understand how many electrons I'm working with. And so what I'm going to do is I'm going to calculate the amount of electrons that I need. So I'm going to look for valence electrons. So for oxygen, which is going to be this guy right here. Let me move up the periodic table for you guys, actually. There we go. So for oxygen, which will be right here, I know that there is 6 valence electrons, and I'm looking at that number right here. For carbon, I know that it's going to be right here, number 4 valence electrons. So I'm looking at the second number, and then sulfur is going to be on the same side as oxygen, so I know it's going to be 6. valence electrons. So now I know I have 6 plus the 4 plus the 6, which is going to be 16 total valence electrons. All right, and now I'm going to go ahead and map out my drawing, my Lewis structure. And I know that everything has to be connected by a single bond. And just so you guys remember, one bond, I'll draw it down here, one bond, one of these sigma bonds, or any of them, is equivalent to 2 electrons. So in every bond, there's 2 electrons. So I just want you guys to know that. And that's really important because at least the way I think about it, I don't want you guys to get confused when we get into the O-Chem aspect of this later, when I'm starting to count all these electrons out for you guys. So don't get confused. One bond is equivalent to 2 electrons. So if I count this as 1, 2, and you're like, hey, there's only one line, what are you talking about? I mean, there's 2 electrons. So just so you guys understand that. And we'll see that here in a little bit when I count up all these electrons. So how many electrons do I have now? So I have 1, 2, 3, 4, right? There's 2 electrons per line, per bond. So now I have 4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so all my electrons are on the paper. Now, the next thing to do is to make sure that each of these elements are stable, they're happy with where they're at. And so what I'm going to do is I'm going to make sure that each of these fills an octet, right? And all of them are neutral. And there's this idea, this concept of formal charge, right? That should be something that we covered. We'll also be doing a lot of practice on that as well. But let's just go ahead and take a look at this oxygen right here, this guy, right? Do we have 8 electrons? 8 electrons is the octet rule. It's happy at 8. It doesn't want to give electrons away. It doesn't want to take or anything. It's happy where it's at. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that's nice. So we're happy there. Now let's look at this sulfur. 1, 2, 3, 4, 5, 6, 7, 8. That's happy. So it has 8, right? There's 2 right here. So it's happy there. Now this carbon, on the other hand, it is not too happy. It only has 1, 2, 3, 4, right? It does not have enough. And so what that means is we need to rearrange our electrons around. And we're going to go ahead and do that by, this will work with me. There we go. By moving this lone pair right here and moving this lone pair right here. Okay? And we're going to have a little bit of a transformation. So now our Lewis structure is going to look like this. All right, we're going to have our 2 lone pairs right there. And we're going to have a double bond. Remember I said every line, every bond is equivalent to 2 electrons. And that's exactly what we did here, guys. We moved these 2 electrons and we moved it. We're going to make it convert it into a double bond. And so, especially with resonance structures, I'm sure you guys are also familiar with that. If you've taken Gen Chem, you can move around, we'll see later, you can move around double bonds around, you can move lone pairs around, just like we did here, right? We took this lone pair and we're converting it, we're moving it to another bond to make a double bond. And so now we're going to do the same thing we did with oxygen with S right here. And we moved the double bond, we moved it as a double bond, so now we have 2. Okay, so now let's count. Do we have 8 electrons per element? Is it happy? Does it fulfill octet? And let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, oxygen is happy, so we're good there. Now carbon, 1, 2, 3, 4, 5, 6, 7, 8. There you go, carbon is also happy. And then sulfur, 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be the structure of OCS, the Lewis dot structure of OCS, right? All of the elements are happy. When I say happy, I mean they have octet, they have 8 electrons, 8 valence electrons. It doesn't want more. It doesn't want to give any away. So we're happy there. So let's move on to H3CN now. So now that we have better understanding, and hopefully we're a little bit caught up with Lewis. Let's move through this one a little bit faster. So with something like this, I like to write down on the paper or the structure exactly how it's written. So we see that H3 is connected to C, N is connected to C, and O is connected to N. So I'm going to use that philosophy and write my structure. And I know that everything has to be connected by at least one bond. And we call one bond, we call that a sigma bond. Just so you guys know, just for your information. So I'm going to start referring it to sigma bonds. So this is a sigma bond right here. All right, this is a sigma bond, this is a sigma bond, this is a sigma bond. One of these is a sigma bond. So sigma bond literally just means one line, one bond. Okay? All right. I'll erase that and redraw it. Okay, and I know that the C is going to be connected to an N, a nitrogen, and an O. Okay? And so now let's count our valence electrons. We know that hydrogen has one valence electron, but there's 3 of them. So we're going to have to multiply that. So one valence electron times however many elements there are. So there's 3, so that's going to be 3. Plus the carbon, which is going to be 4 valence electrons. We saw that here, right? And then we're going to have nitrogen, which is going to be right next to carbon. And that's going to have 5 valence electrons, so plus 5. And then we're going to have oxygen, which is going to have 6 valence electrons, which is going to be plus 6. And when you add all this up, you're going to get 18. Okay? So now let's count all the electrons that we already used when we made these sigma bonds, when we made these connections, right? So remember, one line, one bond is equivalent to 2 electrons. In order to have a bond, you need 2 electrons. So we already have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we need 8 more. So 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, we see over here that carbon is happy. There's 1, 2, 3, 4, 5, 6, 7, 8. So we don't need to do anything with carbon. We're happy there. Nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. All right, so nitrogen is also happy. 1, 2, 3, 4, 5, 6. So oxygen is not happy. So we need to move around some electrons to make sure that oxygen is happy. Happy meaning 8 valence electrons. It fulfills octet. And so what we're going to end up doing is we're going to go ahead and move around electrons so we can move lone pairs around. And we're going to convert this lone pair to a bond, a double bond. So we'll go ahead and erase that and we'll write a double bond there. Okay? And so then you'll see that everything is happy, right? Now the nitrogen has 1, 2, 3, 4, 5, 6, 7, 8, right? We have oxygen, which has 1, 2, 3, 4, 5, 6, 7, 8. So everything is happy. We already saw that carbon was happy as well. So we're all good there. Beautiful. And now also I kind of want to, I'm going to go ahead and erase all of this and keep the structure itself because we're going to go into a little bit of a geometry now. And I just want to make sure that it's not cluttering everything up for you guys. There you go. Okay, so let's take a look at geometry. This is the Vesper. If you need to, go ahead and brush up on that. We're going to try and practice with Vesper right now. And then we'll also have some more practice in the future later on in the video. So we see here for this carbon that there is 2 domains of electron connections, right? There is domain 1, domain 2. So for Vesper, the way I think about it when I'm assigning hybridization is around that singular element, right? How many connections are there? How many electrons are there? How many domains? How many circles, some spheres, clouds? Because if you think about it, if you remember, all of these elements, they have like cloud-like structures with their connections. It's not like a literal line, right? Or it's not like a literal dot. It may be, but it's this idea of a cloud. And these clouds are the way I was taught are individual domains. So this is 4 domains, right? And so when you locate and understand the number of domains, the way I think about it is number of domains minus 1. So right here we have 2 domains, right? So there's 2 minus 1. It's going to be 1. So then there it's going to be sp. Okay. Now for the sulfur, right? We'll use another color. Let's do this color. For sulfur, we have domain 1. We have domain 2. And we have domain 3, right? That's going to be 3 minus 1, 2. So that's going to be sp2, hybridized. Okay, and then same thing with oxygen. Oxygen is going to be the same. So you can try and practice that real quick. Let's do 1, 2, 3. 3 minus 1, sp2. Beautiful. Let's move on to carbon over here. So we know that carbon has 1, 2, 3, 4. 4 minus 3. Sorry, 4 minus 1. It's going to be sp3 hybridized. And so you can associate hybridization. You can use hybridization to kind of help you with geometry, or you can also just kind of look at it. So with a shape like this, and we're taking a look at this surrounding carbon. Let's look at this middle carbon, right? This carbon is written as, and we're kind of ignoring everything else. We can see that that's a tetrahedral shape, tetra 4. There's 4 connections. So we're going to call the geometry around this carbon, we're going to call it tetrahedral. Okay? And I know my handwriting isn't the best, but you get the idea. And then for this middle carbon right here as well, for this guy, all right, we know that it's structured like this. And so this is going to be linear. So this carbon right here is going to be linear. All right, beautiful. So let's go ahead and move on. Let me skip that. Okay, so now we're kind of getting into the beginnings of O-Chem with bond line structures. These are going to be very, very important for you guys to understand. The whole O-Chem is pretty much, if you think about like blocks of like foundation, this is one of the main pillars, right? I mean, every time you see O-Chem, we'll get into it right here, right? These guys, yeah, that might look a little scary. It was a little scary for me when I was doing this a year ago. You'll see that you don't really use Lewis that much anymore. It's more of these bond line structures. And so it's really, really important to understand what they mean. So make sure you guys get a lot of practice with that. We're going to be doing a lot of practice with bond line structures in this video. So make sure to kind of stay along with the video. And as I'm doing the problems, I'll also give you guys a little bit of time, or just pause the video. Do it yourself. And if you get it, amazing. If you don't, no worries. I'm going to be walking through every single problem. And guys, look, there's a lot of problems we're going to be doing. There's a lot of problems. So I'm sure by the end of this video, you guys will be masters, or at least have a better understanding of, going into your next O-Chem class. So let's go ahead and do this. So before we even do problems, I just want to explain to you bond line structure a little bit. So when we see Lewis structures, right? We see structures like carbon, carbon, hydrogen, hydrogen, right? This is just a Lewis structure that I'm making up. Now let's make sure that all these Lewis structures are happy. This Lewis structure is okay. So it's 1, 2, 3, 4, 5, 6, 7, 8. So this carbon is good. 1, 2, 3, 4, 5, 6, 7, 8. That carbon is good. 1, 2, 3, 4, 5, 6, 7, 8. That carbon is good. Remember, each line is 2 dots. Beautiful. So that's why I'm saying I'm kind of counting by 2s. All right. So when we take a look at this structure, it's already taken up a lot of space, right? And when you're dealing with O-Chem, there's a lot of arrows. There's a lot of other stuff that you'll get. I mean, we'll even see it later on in this video. It's just going to be too much on the paper. And it's really important to stay organized. And so what we kind of created this idea of bond line structures. And so for bond line structures, we're pretty much transforming Lewis structures into a bond line structure. That's why in the beginning of the video I was mentioning Lewis structure is super important. So there you go. So this bond line structures, this one right here, that is equivalent to what we just drew as a Lewis structure. So these two are the same. Look at the amount of space it takes up, right? It's a lot more organized. It's a lot compact. It's cleaner. And I promise you, it's not hard to like understand what's going on. So let's go ahead and talk about it right now. So at every intersection, so anytime you guys see like a bond line structure, at every intersection, at every point, there's going to be a carbon. At every start point, there's going to be a carbon. And at every end point, there's going to be a carbon. Okay? And so this is also equivalent to this Lewis structure, like I mentioned, right? This is going to be carbon 1. I'm just numbering it for you guys' understanding of where the carbons are. This is carbon 1. This is carbon 2. This is carbon 2. This is carbon 3. This is carbon 3. Okay? And so that's how you can kind of see how Lewis structures and bond line structures are very, very correlated. Now you may be asking me, hey, Parsa, where are the H's, right? If there's carbons on every one of these points, where are the H's? And so the thing about bond line structures is that you don't draw the H's, they're more implied. And the more practice you do, you'll kind of understand that you don't really draw it out. You're just like, okay, there's an H there. And so let's take a look, for example, for this carbon. This carbon has 3 hydrogens. I'll even draw this a little bit bigger. There's 3 carbons, right? And this carbon is going to have 3 hydrogens. And these are the implied hydrogens, right? 1, 2, 3, okay? And then this carbon has 2 hydrogens. 1, 2, right? And then this carbon, lastly, also has 3 hydrogens. 1, 2, 3. And so, sorry, 1, 2, 3, there we go. And so you may be asking me, because this is a question that I had when I was doing this, how do you know based off of this that how many hydrogens I have, right? If I don't even have this, if I don't have this structure, if we just moved it out the way, and I have a bond line structure just like this, how do I know how many hydrogens there are? And so let's go ahead and try like a little practice problem on that I'll make up. So for something like, let's do something like this, a little bit longer, okay? I want you to go ahead and count for me how many carbons there's going to be. All right, so go ahead and pause the video and try to count how many carbons. Or you can just do it real quick because I'm changing colors. All right, so remember, at every intersection, at every start, and every end point. So this is a carbon. Oh, I wonder what I did there. So this is a carbon. Let me change colors. There we go. Carbon 1, start point. Carbon 2, another carbon right here, 3, 4, and 5. So there's 5 carbons in this, okay? Every start, every intersection, every point, right? And every end point. Okay. Now, I'm sure you guys remember this concept of formal charge, or we talked about it a lot, the octet rule. These carbons need to be happy, right? And I'm sure you guys, when you're Lewis structures, you've seen stuff like this, plus, minus on certain elements, and that tells you the charge. If we take a look at these carbons right here, right? There's no charge on them, which means what? It means that there is no charge, there's neutral charge, and it's happy with its octet. And so if they're happy, right, and we remember, we said that each line is 2 electrons, right? There's 1, 2. Now that means that we have to add our implied hydrogens in order for this carbon to be happy. And so then you start going into the understanding of how do you know how many, right? So I know that if there needs to be 8, and we already have 2, right? 1, 2, 1 line. There you go, 2 electrons. That we're going to need to have 3 hydrogens attached to it. 1, 2, 3. And how do I know that? Okay, well, like I said, 1 line, 2 electrons. So there's 2 electrons right here. That's 2. So another 2, 2, 4. Another 2, 6, 8. Boom, there you go. Now let's do this carbon. Okay? Count the electrons that this carbon already has, right? And if it's easier, how many electrons do we need? This carbon is attached, it has 2 electrons already, 2 on this side and 2 on this side, which means that it has 4 electrons. It's encompassing 4. And so the way I think about it is, how many more do we need? We're going to need another 2. And those 2 are going to be implied by the hydrogens. So that's going to be 2, 4, 6, 8. And remember, I'm putting 2 here because one line is 2 electrons. In order to have a bond, you need it to be occupied by 2 electrons. One bond is 2 electrons. That's what that is. Okay, and so now you may be understanding a little bit more. Okay, now we're kind of getting in the groove of it. We know that there's going to be hydrogens here, right? There's 1, 2, 3, 4, 5, 6, 7, 8. Okay, now same thing with this guy. Hydrogen, hydrogen. And then same thing with here again, right? There's only one bond, right? We need carbon to have an octet. We want it to be happy. We want it to be stable. And if we only have 2 electrons, we're going to need to add another 6. Okay, that's 2. And these are hydrogens. And when your bond line structures, I would recommend starting out to draw the hydrogens, because it helps you with a lot more practice. You get a lot more practice with it, so draw them out. All right, so now that we kind of have a basic understanding of it, let's go ahead and do some practice problems, right? It's really important to do practice problems. And when you see Lewis structures like this, what do we remember about bond line structures, right? The H's don't even show. So when I think about it, I quite literally get my highlighter out, and I just, to help me visualize it sometimes, go ahead and just highlight the carbons, okay? And that's how you know the basic structure or representation, like the visual representation of what the bond line structure is going to look like. So we have a carbon here. It's going to be the, actually I'll draw it. It's going to be the bond line. Okay. We know there's a bond to another carbon. We know that there's a bond to another carbon and a bond to another carbon. So we're going to draw. I'm going to show you the transformation. Okay. Right? And you may be, telling me, hey, Parsi, you forgot a double bond. Yeah, you're right. I did. So we're going to go ahead and add the double bond right there. And so if you see it's the same structure, but bond line structures, as you see here, it doesn't implicitly show the carbons, because the carbons are implied where? At every point, at every intersection, and at every endpoint. Okay? And so we're going to go ahead and transform this. So now we know that if there's a carbon at every start point, there's going to be a carbon right here. I'll draw little circles on it to help you guys kind of visualize where the carbons will be. But on your tests, quizzes, homeworks, and you're like churning in work, don't draw the dots, because that's not technically how you're supposed to draw it. I'm just writing it so you guys can see. There's going to be a carbon there, so that's carbon 1. It's carbon 1. Okay. Carbon 2 is going to be a point. We're going to have carbon 2 right here. Carbon 2. That's carbon 2. Carbon 3, we're going to draw as a line up. It's going to be carbon 3. And then carbon 4, we don't need to add anything else, because remember, there's going to be carbons at the ends. Okay, so there you go, guys. That's going to be the structure of that. And you may also be asking me again, hey, well, how about this guy right here? How about this double bond, right? We didn't incorporate this double bond. We only have a single bond to carbon 1 and carbon 2. So let's go ahead and add that as well. And with double bonds, the way you represent that is you just literally draw another line right here. There you go. That's all you do. You just draw another line. Make sure you guys can see that. Oh, there you go. And so that's it. That's that. And we can continue to do that with all the other ones. And you can see how this structure is very similar, right? Look at the pattern of this, right? We have a double bond right here. You see that pattern? It's quite literally the same as this. It's the same pattern. And so that's why highlighting helps me out a lot. And you'll see why it helps me with examples that look like this or that look like this when we're converting these into bond line structures. Okay. So let's do a problem like this guy right here. O and H. Okay, and this is asking us to convert this back to a Lewis structure. So now that you guys have a little bit of an understanding of bond line structures, I want you to pause the video and see if you can convert it back to a Lewis structure. So instead of going from here to here, I want you guys to reverse it. I want you guys to go from here to here. And this will kind of help you understand how Lewis dot structures and bond line structures are very, very similar. It really helps you to go from one to the other. So go ahead and pause the video and do that. I'll go ahead and start. So for this guy, what helps me is drawing the carbon. So we know there's start points, intersections, endpoints, right? We know that every single carbon has to have an octet. There's no charges, there's no pluses, there's no minuses indicating formal charge. And there are problems where that's going to happen, and that'll be later on in the video. And so that's how we know that these carbons need to be stable. They need to have their octet. So what does that mean? So that means we're going to need some hydrogens. So this already has 2 electrons, right, from this bond. So we're going to need another 6. It's going to be from the hydrogens. That's 1, 2, 3, 4, 5, 6, 7, 8. Remember, one bond is 2 electrons. Okay, the carbon, we did this example before. 2 hydrogens, right? There's 2 electrons here, another 2 here, to be total of 8. So that's how we know we need 2. Same thing with this guy. Now for this carbon, it's attached to a couple more things, right? This carbon has this bond, which is 2 electrons. Another has another bond, which has 2 electrons. And it has this bond, which is 2 electrons. Now you may be wondering, hey, what does this mean? What does this little triangular thing mean? And also, you're also going to see other examples with dashes. And so these indicate a 3D shape. Okay, that's not something that I'm going to talk about right now. I think I'm not entirely sure if Gen Chem covers this. I don't really remember, but that's something that I'll talk about later on in videos. That becomes important a little bit later on in O-Chem. But it's really good to kind of understand what it means now so you have a basic understanding. I don't want to confuse you guys right now, so I won't talk about it. For now, just think of it as its own little bond. It is its own bond, so don't really think about the 3D shape. So we have 3 separate bonds, right? 3 individual bonds to this carbon. What does that mean? That means it has 1, 2, 3, 4, 5, 6. So if it has 6 bonds, how many more do we need? We need 2 more, 6 electrons. We need 2 more to hit that octet. So we're going to go ahead and add just 1 more hydrogen. Just 1 more. And if we count again, 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. So that's how we know we only need 1 more hydrogen. And when you're doing your practice problems, literally count it out. I still to this day count it out when I'm doing my hydrogens. It helps me. Okay, so let's convert this back now to a Lewis. And now that we have all this information, it's a little bit easier to do that. Let's do another color. Let's do green. So we know carbon is going to be here. Let's just draw the carbon, all the carbons out first. Okay. And we know that this carbon right here, right? I'll even number them. Carbon 1, 1, 2, 2, 3, 3, 4, 4, and carbon 5. 5. Okay. I know that that carbon is attached to an O. And that oxygen, even though the line isn't specifically shown, is connected to an H, is connected to a hydrogen. So I'll go ahead and add that. Okay. And so now we need to draw our hydrogens in, right? All the hydrogens that we drew, we also need to add that. Oop. I don't know what color I did. Carbon. Okay, so let's go ahead and draw all the hydrogens that we drew. So that's going to be carbon 1 is 3. This is going to have, I'm going to erase the 2 that's in the way. But just don't forget that this is carbon 2. Carbon 3 is going to have how many? 2 as well. And then carbon 4, this carbon right here. Remember, that's that one H. That's that separate H. So it's getting one H since it's already connected to 3 other things, right? It's connected to this guy, and this guy. So we'll need one more for that. And then last but not least, our carbon 5, which is going to have, I didn't draw it here, but it's going to have 3 electrons. Same logic as carbon 1, right? With the octet rule. And don't forget, you guys may think, okay, we're all done now, but we're not. We're missing some lone pairs on this oxygen, right? This oxygen does not have octet yet. That's really important. So how many does it have so far? So it has 2 from this bond, 2 from this bond, right? It has 2 electrons already. And so, here, let me draw it out in a different color so it's easier to see. So we have 2 electrons and 2 electrons, 4, right, from these bonds. So we need another 4. We're gonna have that as lone pairs. There you go. So that's going to be the structure of that guy right there. All right, let's move on now. I'm going to go ahead and make this smaller so it doesn't crowd the problem below it. All right. Now, when we're looking at something like this, you guys are going to want to do the same thing, right? Get your highlighter out. Pause the video, go ahead and take a second to write this down on your paper, your iPad, or whatever you're using, and try to convert it into a bond line yourself. So pause the video and do that. I'll go ahead and do it right now. Just remember, get your highlighter out. Where's all the C's at? There they are. Am I missing any? No. Beautiful. And so first thing we're going to do is we're going to draw that intermediate step, the step before the bond line. And I'm only writing the intermediate just so I can show you guys how we're getting to the bond line structure. It's not like a thing that you really like you actually do. There's no like, at least in this process, the intermediate step is just for me to show you guys how I'm getting from part A to to the end point. So from start to end. So it's not something that you guys have to draw out or your teachers are going to ask you to draw out. Unless they do. All right. So we're going to have our carbons, right? So we have carbon right here, carbon right here. We're going to have a carbon up here, a carbon here. We're going to have a triple bond to a carbon, another carbon, carbon. 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Make sure you have all your carbons down. Okay. Now, just literally all we do is copy this shape, right? So now that's the little intermediate form before we get to the bond line structure. And so when we're drawing the bond line structure, just remember at every point, every start point, every intersection, and every end point is a carbon. So we know that there's going to be a carbon right there, right? This is going to be carbon 1. Here, actually, let me do this in another color. Start point. This guy right here, that little dot that I drew, that's carbon 1. This is carbon 1. Okay. This intersection, carbon 2. Carbon 2. This point up here, that's carbon 3. This is this carbon. Now, I'm going to go ahead and draw the rest of it out so I can show you guys what the deal with triple bonds are, because I was really confused when I saw triple bonds in O-Chem starting out. I was like, hold up. If we just said that there's carbons at every start point, every intersection, every end point at these points, there's no points here, right? There's no like intersection. There's no endpoint in this area. So what's going on over here? So we'll talk about that here in a second. But for now, you guys, we do see that there is a carbon 1, carbon 2, carbon 3, right? This guy right here. And so carbon 4, when you look at double bonds, triple bonds, just kind of think about it as the start and end point as well. Think about it in the start and end point of where the triple bond begins, right? So we're going to have a carbon here, of course, right? Like I mentioned, the rule still stays the same, every start and end point. But also, now there's a carbon at the start point of this triple bond, and and a carbon at the end point of this triple bond. Okay, so there's a carbon start at the triple bond place, and then a end carbon at the end of the triple bond, and another carbon at the very end of the whole thing. And so for a Lewis structure, that would look like this, guys, right? Carbon 1, carbon 2, carbon 3, and carbon 4. And so you can kind of see how the point, like if you just erase that and you just connect these, don't forget, those carbons were still there. Okay? So that's how I think about it. I know it was a little tricky, but I hope that made a little bit more sense. So going based off of that, right, we now know that there is going to be a carbon right here at this point. That's going to be carbon 4 at this point as well. Remember, at the start of the triple bond, at the little beginning of it, and at the end of it, right here, is going to be carbon 5. It's going to be carbon 5. And then carbon 6, remember, that's just our basic rule at the intersections. And then at every point as well, carbon 7. Carbon 7. And so there you go. This guy right here is your end bond line structure, minus all of the little periods and the numbers. I mean, you can add that. I'm sure my teachers would not be upset if I drew this out. I just kind of drew it out to show you guys the numbers. It's just a little bit more timely on like testing quizzes, so nobody really draws them out. But in the beginning, I would. Just so you guys really, really solidify the understanding of these bond line structures. All right, now let's take a look at this guy. This is a ring, right? It looks like a little bit of a ring. Let's shrink this down. And so we're going to do the same process, guys. We're going to go ahead and take our highlighter out. We're going to go ahead and highlight all the carbons. But don't forget, it may sneak up on you. So many people miss questions, including myself, because there's so much stuff on the paper, all these H's, that this Cl, this chlorine, becomes almost camouflage, right? It's hiding under all these hydrogens. And that's still something that we need to add in our bond line structure. Bond line structures, they're really the only thing, as far as I've seen so far, that you don't incorporate or include are the carbons, right? They're all implied. So all of these intersections and all that stuff, those are all implied. And then you don't add the hydrogens as well. Those are implied. But all these, like the halogens or any other element, you'll see later, like down here, you see nitrogen, you see oxygen. Those are stuff that you still have to add because those are not implied. So make sure that little chlorine doesn't, sneak past you. And so we're going to go ahead and draw a little intermediate, right? Just the carbons by itself. Just the stuff that we're going to be adding to the bond line structure. Okay. And, well, now we know that every intersection, there's a carbon. Okay. And then we have a chlorine down here. Right? We're literally copying this shape. And if we go back and we're like, you guys are a little bit confused about where all the carbons are. There's a carbon right here. So carbon 1. Remember, every point, every intersection. Carbon 2. Carbon 3. There's another third carbon here. Another carbon here. 4. Another carbon here. 5. And lastly, another carbon here. 6. So that's the bond line structure. This guy. Without the carbons written, of course. And you have your Cl. Okay? Okay, beautiful. Let's see. Let's go ahead and skip this guy. Let's do... Should we do it? Yeah, let's just do it for practice. Why not? I'll take a little quick drink. So, for this guy over here, we know that there's going to be carbons coming out. There's carbons here. So this has how many electrons around here right now? 1, 2, 3, 4. We need another 4. All right, so that's going to be hydrogens. That's going to have 8 now. This carbon right here, remember every intersection, there's 1, 2, 3, 4, 5, 6. So that means we need 2 more. And 2 more we can do with 1 more hydrogen. And this carbon right here as well. There's 1, 2, 3, 4, 5, 6, 7, 8. So this carbon is good. It's happy because of this double bond with O, with oxygen. And so we don't need to add or worry about the carbon there. We don't need to add any hydrogens, okay? And so when we're converting this to our Lewis dot structure, right, we're going to have H, O. Make sure you guys can see it. Yeah. We're going to have it connected to a carbon that is connected to 2 other hydrogens. And then this carbon is going to be attached to another carbon. Okay, that carbon has a hydrogen. Make this a little neater. And it also has a nitrogen, and this nitrogen has 2 hydrogens attached to it. And then it also has another carbon with a double bond to oxygen. And then that carbon is connected to O, which has a connection to hydrogen. And so that is going to be the kind of the skeleton of your Lewis structure. And so let's go ahead, and now we have to add all the lone pairs to this diagram. And so before I do that, I just want to make sure that we are understanding where all of these carbons are coming from, right? So this carbon right here, this guy, carbon 1, this is coming from this carbon right here. That's carbon 1 right there, okay? As you see, this carbon, the one I circled right there, here, I'll make it a little bigger. This guy is connected to what? What is it connected to? It's connected to 2 hydrogens, which we see. Hydrogen right here, another hydrogen. It's also connected to an oxygen, and then oxygen is connected to a hydrogen. So that's where that's coming from. Okay, now the other carbon, this carbon, carbon 2, is coming from this guy right here. And what is this connected to? What is carbon 2 connected to? It's connected to 2 other carbons. Right, there's a carbon 3 here at the intersection, and which we see, and a hydrogen as well. And it's also connected to a nitrogen, and that nitrogen is connected to 2 hydrogens. And then carbon 3, our last carbon, is this guy over here. This carbon 3 is connected to an oxygen. It's also connected, or double bonded to an oxygen. And it's connected to another oxygen, and that oxygen is connected to hydrogen. So that's kind of where all these carbons are coming from. So I just want you guys to be able to see that. But let's go ahead and add our lone pairs. We know that everything here needs to be octet. It needs to be happy. There's neutral charge. So there's going to be lone pair here, right? There's 1, 2, 3, 4, 5, 6, 7, 8. Every line, every bond is 2 electrons. Carbon is 1, 2, 3, 4, 5, 6, 7, 8. So this is good. This carbon, 1, 2, 3, 4, 5, 6, 7, 8. That's nice. That's all happy. Nitrogen, 1, 2, 3, 4, 5, 6. That's not happy. It needs another, it only has 6 electrons. It wants another 2. So we're going to go ahead and add a lone pair. This carbon in the middle has 1, 2, 3, 4, 5, 6, 7, 8. So that's happy. And this oxygen, 1, 2, 3, 4, only has 4, so we need to add another 2. 5, 6, 7, 8. There you go. So that's going to be your Lewis structure of that guy. Go ahead and shrink this down. All right. Now our last guy on converting, we're not going to do an intermediate step. We're just going to go straight through. Okay. Hopefully we got enough practice and understanding. Let's go ahead and try to do it without the intermediate. So go ahead and pause the video and just go ahead and try this out yourself. Do the highlighter, do whatever you need to do. I'll go ahead and do it right now. So we know at every intersection there's a carbon. And we're just going to pretty much copy the general shape, right? And we go back, we see these double bonds. And so we only have single bonds. We don't have double bonds anywhere. So it's as easy as just going back and adding it, right? There's a carbon between, there's a double bond between these two carbons. There's another one here. And there's another one here. So there you go. Those are the double bonds, right? And if you want to visualize it, carbon all around. Just like we see here, carbons all around. All right. So for these, this says, for the following compound, determine, so we're going to do some formal charge work. All non-bonding electrons are shown. For carbon atoms, assume 0 charge. Write the assumed number of hydrogens. Okay, beautiful. So let's do this problem. I'll go ahead and zoom into it for you guys. All right. So what it's asking us to do is draw all the hydrogens in, all the assumed hydrogens. Remember, in bond line structures, what's not written? The carbons and the hydrogens. So if we know there's a carbon at every intersection, okay, and we know that every bond is 2 electrons, let's just add in our hydrogen, right? This carbon, this guy right here, has 2 bonds around it, so that's 4 electrons. So we're going to need another 4. So remember, when I say another 4, 1 bond, 2 electrons. I'll actually just keep this up. This carbon here, the same thing. These are all the same. So they're all going to need 2 hydrogen bonds, which is 4 electrons, to reach that octet. Now this guy in the middle, this carbon right here, this guy has 1, 2, 3, 4, 5, 6, right? So that means we only need 1 more hydrogen sticking out to have the 8. And then this carbon is just the same as all the other ones. And so there you go. That's how you do that one. It's not too hard, not too bad. We did miss a carbon, this guy right here. But this guy we don't need to worry about because there's 1, 2, 3, 4, 5, 6, 7, 8 because of that double bond. And so that has 8 total total electrons around it. It's octet, it's happy. We don't need to worry about it at all. Nothing else to add here. Now let's do a ring. So with carbons like this, remember the rings, every intersection. And don't have these little lines on the side scare you. Those are just double bonds. We just drew those up here, right? There's double bonds here. We drew them here, right? They're just double bonds. So we count those as electrons as well. So this carbon, right? This carbon has 1, 2, 3, 4, 5, 6. So instead of 2, we just need 1 more hydrogen, 7, 8, to have an octet. Okay. Now let's look at this carbon right next to it. It's also sharing this double bond. So that means there's 1, 2, 3, 4, 5, 6. It needs 1 more. 7, 8. To fulfill that octet, to have that 8 electrons around it. This guy, 1, 2, 3, 4, 5, 6. Same thing, guys. So you're going to see all these are the same. There you go. All right. Now let's do this guy over here. Where are all my carbons? At every start point, end point, intersection. This carbon only has 1, 2, so we're going to need 3 more hydrogens. All right? 1, 2, 3, 4, 5, 6, 7, 8. All happy there. Let me rewrite it so it's neater. This carbon in the middle has 1, 2, 3, 4, 5, 6, 7, 8 because of that double bond. So that's 8 electrons. So anything we see here, these are all the same, right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Those are all happy. We don't need to worry about these carbons with these double bonds right here because they have 8 electrons around them. It's happy with this octet. This guy, on the other hand, is the same as the other one that we saw here. It only has 2 electrons around it. It's sharing those 2 electrons. So we're going to need another 3 hydrogens, implied hydrogens, to make sure it's 8. Now we're not done, right? It's also asking for formal charge. And so we need to make sure that all of these have the right number of formal charge. And so with formal charge, let's use this periodic table down here, right? Let's see what we have. We have a nitrogen right here. Nitrogen has how many valence electrons? It had, let's find nitrogen first. Nitrogen is right here. It has 5 valence electrons, right? This 15, we only use the 5. So nitrogen has 5 valence electrons. And your teachers are going to get a little bit upset with me here. So make sure that you don't repeat what I tell you to them. There's an equation for formal charge. I'm sure you guys know. But to be quite honest with you, every time I calculate formal charge, I'm not going to be using the equation in my head. That's just, I don't know. For me, I like to be fast and efficient because with my exams, there's a lot of O-Chem questions, a lot of time that you have to spend on other parts of the question. So I don't really have time to use the equation. I forgot the equation. I couldn't even tell you guys right now. But it's pretty simple. Just go ahead and Google it. But let me tell you the way I do formal charge. So it's pretty much the same. But I know that, for example, let's work with this nitrogen in the middle. This guy right here. We'll go ahead and take out all these other carbons. This nitrogen, we know, has how many valence electrons? We just saw in the periodic table has 5. Okay? And I subtract everything else. I add all of the lines and the dots. Okay, so if we go onto this nitrogen, this single guy, we have line 1, 2, 3, 4. There's 4 lines. So 5 minus 4 is what? 1. So that's how I know this carbon has a +1 charge. We don't really need to add. We don't add the 1. So we just keep it like that. So that has a plus charge. Now, for the valence, for the formal charge of this guy, the nitrogen right next to it, right? We still have the valence electrons. We still have 5 valence electrons. But now we have dots. Now we're introducing lone pairs. And so, make sure you guys can see it. We're introducing lone pairs, right? Make sure it's centered. Come on. There we go. We also have some lone pairs, but we also have bonds as well. So it has 1, 2, 3, 4 dots, 5, 6. Remember what I said. The number of dots, lone pairs, electrons, plus the number of lines. 1, 2, 3, 4, 5, 6. And I'm not saying that, yes, one bond is 2 electrons. That's how it's written. But when I count formal charge, I'm counting this as 1, not 2. Just for formal charge, guys. Just for formal charge. I don't want to get you guys confused. So back at it again. 1, 2, 3, 4, 5, 6. 5 minus 6 is -1. So that's how I know this guy is going to have a formal charge of -1. That's how I do lone pairs. I'm sure you guys are experts or good at lone pairs and formal charge and all that stuff. So we won't do too many problems specifically on that. I kind of want to do a little bit more problems on, we'll do a couple more actually. I want to do more O-Chem problems. Determine the formal charge of the atoms. So if we go back, let's do this guy first. We don't need to do too many of these actually. We'll just do one of them. Or we'll do 2. Let's see. Yeah, we'll do 2. Formal charge isn't too bad. With the new method that I showed you, it should be pretty fast. So we're looking at this carbon right here. Remember, at every intersection, there's a carbon. So carbon. And if we go back to our periodic table, we see that there is carbon right here and has how many valence electrons? 4. We're looking at that second number. It's a 4. And so going back to our problem, if we know that there's 4 valence electrons, 4 minus the total number of lines plus dots. So there's 1, 2, 3, 4, 5. 4 minus 5, negative 1. All right, so this carbon right here has a formal charge of -1. Okay, now moving on, let's do something like this. So oxygen, going back, has valence electrons, 6 valence electrons. So we know that 6 minus lines plus dots, 1, 2, 3, 4, 5, 6. That's neutral. So we don't need anything. That's happy. Now this carbon over here, we know that there's 4 valence electrons in carbon. We saw that on the periodic table earlier. And lines plus dots, 1, 2, 3, 4, 5. That's going to be -1. It's going to be negative formal charge. Okay. So that's the little method that I use. And these are the same problems that we just did. I don't want to spend too much time on formal charge. So we're going to go ahead and skip those. We're going to do something like this now. So this looks a little bit scary, but I promise you, when you guys get more practice, and even you guys may be a little bit more comfortable with it now, it may seem like a lot of stuff, but it's a lot of stuff that you guys already know. So all of the problems that we were doing, this is like the test, right? To make sure to see if we know everything that we learned above here, right? Because we just did a lot of bond line structure practice. We did formal charge practice. We did adding the implied hydrogens. And so this is kind of the test here. So this is asking you to draw in the formal charge, the implied hydrogens, and electron pairs for each structure below. So going through this guy, right? Going through this guy, we see that this nitrogen is connected to, remember, every endpoint, carbon right here, carbon right here, carbon right here. And you may say, okay, how about this point right here? That's not a point. It's just, that's showing the connection from nitrogen to a carbon, right? So that's not like, you don't say there's a carbon right here, because that doesn't make sense, right? But this is just literally showing the bonds. This is showing this. That's what that's showing. This little area right here. Okay. So if we know that there's carbons around here, we know that this only has 2 electrons, 1 bond. We're going to need another 3. All right, we practice. I would honestly pause the video again, and I would try to do this one myself too. We know that this carbon right here has 2 bonds, so that's 4 electrons. So we're going to need another 4, which is represented with these 2 bonds. This carbon in the middle is going to have 1, 2, 3, 4, 5, 6, 7, 8. So that's happy. We don't need to add anything else there. Now this oxygen, we're going to need some lone pairs, right? Because this has 1, 2, 3, 4, where we're missing some. We're missing 4 electrons. So we're going to add 2 lone pairs to make sure that it fulfills that octet. And for these carbons, right, there's carbons all around. 1, 2, 3, 4, 5, 6, just 1 hydrogen will do. 7, 8. And then same thing with this guy, 1 hydrogen will do. With this guy, it's the same scenario as here. 1, 2, 3, 4, 5, 6, 7, 8. So that's this carbon is happy. We don't need to add anything here. Now for this S, this sulfur, we're going to go ahead and see how many electrons it has. 1, 2, 3, 4, 2 more, 6, 7, 8. This carbon needs 2 hydrogens. We're getting the hang of it now. This nitrogen has 1, 2, 3, 4. And although the line isn't necessarily shown, there is a line, there is a bond between hydrogen here. And so this is going to be 1, 2, 3, 4, 5, 6 bonds, electrons. So we're going to need to add a lone pair on this guy. If that didn't make sense, draw the Lewis structure. So this Lewis structure is carbon here. It's attached to a nitrogen, another carbon, and then a hydrogen. That's what this is. Okay. I'll go ahead and erase that. Make it cleaner real quick. Oh. All right, and then we said lone pairs. We're going to add lone pairs on this. There's 1, 2, 1, 2, 3, 4, 5, 6, another hydrogen, or lone pair, so 7, 8. Okay, and then this oxygen and nitrogen on the side. Well, actually, there's this carbon here, and a carbon here. Almost forgot. This is going to take how many? You got it, 3. This carbon has 1, 2, 3, 4, 5, 6, so it only needs one more hydrogen. Now, this oxygen has a -1 formal charge, right? So what does that mean? That means, well, we know that oxygen has 6 valence electrons, right? We saw that before, right here. There we go, switched. Right here. And we know that we need to end up with a formal charge of -1. So what would add that? That would be, what, 7, right? And so we're going to need to also make sure that not only is it -1 formal charge, but it's also an octet. And so there's already a bond right here between oxygen and nitrogen. So that's 2. So that's 1, 2 electrons, 3, 4, 5, 6, 7, 8. So first, let's make sure, does it fulfill octet? Is it happy? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. And let's calculate formal charge, which is number of valence electrons. So 6 minus, the way I think about it, lines plus dots. So 1, 2, 3, 4, 5, 6, 7. -1. So that's how you know. That's how you can check yourself. And then for nitrogen, nitrogen is one of those exceptions that is happy with not having its full octet. There's a couple elements that are like that. So this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Well, never mind, actually. This nitrogen has its octet already, but it has its +1 formal charge. So we don't need to add anything, because why? It has its octet. But if we're confused about the formal charge and we want more practice, we can just go ahead and do it. Nitrogen has 5 lone pairs minus all of the lines, 1, 2, or lines plus dots, 1, 2, 3, 4, which is +1, and that's where we see here. There you go, guys. That's your first one. That's the big test. Hopefully that makes a lot more sense now. We're going to get into some more hybridization problems. So I think we're getting close to the end a little bit before we go into resonance. So let's do some more hybridization. This should still be review. So C1 we have over here. Look up. C1 is going to be where? Let's find it. Carbon 1. Carbon 1 is right here. So carbon 1, there's a carbon at every intersection, right? Look at that. Carbon at every intersection. And so we're thinking about hybridization. We need to go back to those domains that I was mentioning earlier. How many domains does this carbon have? This electron domains. There's 1, 2, 3, 4. Okay, there's 4 connections to it. And lines and dots are still the same thing. They're still domains. So if you see like something like a lone pair, let me see if I can find an example. Like, for example, with this guy, this bromine, there's 1, 2, 3, 4 domains around it. So you still count the lone pairs as domains because they're clouds. It's a cloud of electrons. So that's what we're going to be going off here. There's 4, 4 minus 1, 3. So it's going to be sp3 hybridized. Okay. Carbon 2, which is right here, right? That's carbon 2. This has 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, so this doesn't have octet. but there's no formal charge. And so that means we need to add another hydrogen. Right? When you guys are doing this, your hybridization, make sure you guys are filling in all the implied hydrogens. So there's an implied hydrogen right there. And so because of the that hydrogen, it's not sp2, but it's sp3. Why? Because there's 1, 2, 3, 4, this fourth electron domain. So 4 minus 1, 3. sp3. And so now we're getting the hang of it. We'll do one more. Carbon 3 right here. This has 1, 2, 3, 4, 5, 6, 7, 8. So there's nothing else we need to add. It has 1, 2, 3 domains. So 3 minus 1, sp2. And I don't want to spend too much time with reviewing. It is important though. So we'll do carbon 1 and carbon 2 for molecular geometry. Actually, I think they're the same. We'll do carbon 1 and carbon 3. If we go back to carbon 1, which was, where's the carbon? Right here. We see that there is this tetrahedral shape. There's 4 connections. So that's exactly what the geometry is going to be. It's going to be tetrahedral. Now for carbon 3, which is right here, right? We didn't need to add any hydrogens. We didn't need to add anything. And so it has this triangular shape, right? So that's going to tell us that it's going to be trigonal plane. Oh, there we go. Okay, and make sure we don't get trigonal planar confused with trigonal pyramidal, because I know they can kind of get swapped. At least they used to for me. So trigonal planar is this concept where you have, right, this shape right here. Trigonal pyramidal, this is planar. Pyramidal is when you have lone pairs introduced, and it kind of looks like that. Also, if it helps, you can go ahead and look it up as well. That's going to be pyramidal. For your Vesper shapes. It's been a while since I've done those as well. But good to know. We have a lot of practice with implied hydrogens. I want to get into some resonance. Dipoles, we should know from Gen Chem. Yeah. We've converted a lot of the Lewis structures. This is a little bit harder, maybe. So we'll just do one of these. We'll practice with this guy. So we're going to go ahead and convert this. First, let's go ahead and draw all the carbons that we have, that we know about, to help us. And there's also hydrogens. So there's 1, 2, 3, 4, 5, 6. There's hydrogens here. So I'm going to stop counting. We're getting into the groove of it. And sometimes you'll even still see me counting, just to double check myself. I just have PTSD from getting points taken off by not adding a singular hydrogen in a problem, and so many people have had that mistake too. So I've just kind of got into the habit of counting all of them. And so now when we have that, we're going to have a nitrogen here, connected to an H and H, nitrogen. Make carbon here, right? We don't really need that. There we go. There's a carbon in here. It's going to be double bonded though. Another carbon. Double bonded to another carbon. Another carbon. And these carbons are connected. This carbon is connected to this carbon. And that carbon is going to be connected to an oxygen, and it's going to be connected to another oxygen. Carbon. There we go. Okay. And then we can go ahead and add all our H's in. Oh, I forgot the double bond here. All right, beautiful. And then go back and add your lone pairs. There you go, guys. That's the Lewis structure. Now, if you're looking at this and you're like, whoa, what just happened. No worries. I'll go over it real quick. I'll label all the carbons for you. Make sure it fits. Okay. So let's look at this guy. Let's look at this ring first. Okay, ignore the other side. This is what this ring is. Actually, let me do you guys one more. Let me write this back down. Let me highlight it. So that's one ring. And then the other ring is right here. Okay. So if that kind of helps you visualize it, and I'll really quickly carbon 1, 1, 2, 2, double bonded, 3, 3. This carbon is attached to a nitrogen, 4, 4, 5, 5, 6, 6, and then we have, let's just say this is 7 and 8. Okay, this is oxygen, oxygen. There you go. Okay, oh, functional groups. Okay, well, this is one of the beginnings of the whole memorization of O-Chem. So I'm sure going into O-Chem, everyone's heard rumors. We all go around and ask. I definitely did. And the first thing that I get told is there's a lot of memorization in O-Chem. And so this is kind of where it starts. It hits you right off the bat. And the memorization is functional groups. Now, for functional groups, this is how I memorized it, guys. I just pretty much wrote. There's more functional groups you're going to need to know later on. But for the ones that I had to know in the beginning, and I'm sure your teachers will provide you with the list, split it up, chunk it up. For example, if you have like, I don't know, 15 or 25 or something, do 3 at once, right? Memorize the first 3. So for example, I memorized in chunks of 4 or 3 right here. And not only did I draw it out, like examples, I also kind of did a really short sentence summary of kind of what it is. And so when I did it in chunks, I just continuously repeated it, and that helped me a lot. It also helps me to not just memorize and to understand. So that's why I write these like single sentences out so I can understand, because when I understand, I have a higher probability of knowing and being able to identify it than just purely memorization. Something else that's worked for other students is flashcards, but I always, including myself, we always go to our professors and we're like, what's the best way that you can memorize these? And there's no, like, in my opinion, like a secret sauce. You just have to kind of take the time to sit down and either draw in your flashcards or do it like how I did, write it out, and do like practice problems with it to truly understand and memorize. But if you guys do have a secret sauce, please, provide it for me, because obviously I'm going to have to memorize a lot more and provide it for other students and maybe you in the comments. And yeah, so let's go ahead and do a problem like this. So hopefully, if we've memorized functional groups, I would either skip this section of the video and go to the resonance area, because that's what we're going to be doing later. And then once you're done with the video, go memorize your functional groups, come back, and then do the problems with me and see if you remember. If you do know it, or you kind of know it, beautiful, then let's just go ahead and do it together. So looking at this guy right here, right, we see that there's a nitrogen. So that's going to be an amine, right? There's a nitrogen connected to an R group. R group are like carbon. So like this is an R group, all like everything else, right? So it's connected to 3 different carbons. We also see what do we see here, guys? Actually. Right. Oh. What do we see here? There's a CO, a carbonyl group, is what we call that, carbonyl group, a CO. There's a carbon here, double bonded to an oxygen. And so this is going to be what we call an ester. Associated with this oxygen. So that's going to be an ester. Then we have one more. We have this aromatic ring. Aromatic ring. Beautiful. Let's move on. Let's do another one. So right off the bat, we see double bonds, triple bonds. So we can just quickly say that's going to be an alkyne. I feel like I'm not writing these or the spelling is wrong, but you get the idea. And then alkene for a double bond. Yeah. And then for this guy, what do we have? We have a R group, right? These are the R groups, just everything else. We have a carbonyl group, which is a C double bonded to an O. So that's going to be a ketone. There you go. Let's do another one. So everything that says A, we're going to skip the hybridization, all that stuff, since we just did practice problems with that. But let's go and let's do everything that says A. That's where we're going to want to identify the functional groups. Okay, so here we have a ketone. We have another ketone right here. All right, and then we also have a carboxylic acid. And then what else do we have? I think that's it. Those are all the A's indicated. Okay, looking at all the A's again, we have a nitrogen here. We only have one more of these guys. So this is going to be an amine because you have a nitrogen with around R groups. And this guy is going to be an ester. Make sure you don't confuse an ester with an, is it ether? I think it's ether. Hold on, let me double check. Yeah, it is ether. Ester with ether, right? These are two different things. In ether, it looks like this. Okay, it's an oxygen with R groups. That's not what an ester is. Ester is what we just saw before, right here. And ether is up here. Oh, totally didn't show you guys. So ether is the oxygen that I was showing you guys. And ester is down here. And that's what we saw with this practice problem. So that's an ester. I know it's really easy to mix it up. Okay, this right here. That's it, one. We got another one right here. So we know that this is what? An alkene. And what is this? We have an OH. There's no double bonds. There's nothing else, so we know it's an alcohol. All right, let's keep practicing functional groups. So we have an OH. So just, if I were you, for every one of the next, we're going to do two of these. We'll do two or three. But for this section, for this number 14 section, I would pause the video again for each of these and try to do it yourself. It's really, really helpful and beneficial if you just like fail and then you realize what you messed up on and then you'll remember it next time. So I would pause and try it again. But we have one right here. So that's going to be an alcohol, right? Because of that OH group. And then we're going to have another one. We have this oxygen connected, double bonded to a nitrogen, and then an R group. So we have nitrogen, we have our R group, remember that carbon group, and then we have this CO double bond. So this is going to be what? An amide. Okay? And then we got one more. This guy right here. Just a nitrogen connected to a hydrogen and an R group. This is going to be an amine. Make sure it's, because I spell it Right, so you guys don't get confused. This is an amide. Another thing easy to mix up. All right, this guy over here. So we have two. You have a bromine, bromine, two bromines. And these are going to be called alkyl halides. And you can kind of just understand it in the name. When I was saying, like, understand what these functions are instead of just memorizing. What's an halide? Halogen. Halogen is all of these these guys over here. Right? So it's all on the periodic table. I hope I didn't confuse you guys. Halogens are these group. That's right. All right. Let's do another one. Okay. We have a carbonyl group. Remember, carbonyl is C double bonded O. And it's attached to a single hydrogen in an R group. R group is just the rest of the thing, but the rest of the thing has to be like carbon. So there's a carbon right here. And so that's how we know this is going to be a what? Just forgot the name. Oh, yeah. Aldehyde. There we go. And that's the only thing that's going to be there. But don't forget, don't let the double bond slip past you. There's going to be, actually, let me just change the colors. There's going to be an alkene associated with this. Okay, there you go. Not too bad. I think I spelled that wrong too. Sorry. Okay, with this guy, we have another carbonyl group. We have an OH in the R group. This is going to be a carboxylic acid. And we have a couple things on this guy. We also have another aromatic ring. Okay. And then we also have what? We have a ketone right here. There you go. All right, next. We have a couple things here as well. We have an OH group. That's going to be what? An alcohol. You guys were able to see this, right? Hopefully. Okay. Alcohol. Going back here, we're going to have another one. This guy. What is that going to be? It's going to be another ester. Okay. And ester is written like this. When you're going and studying, and that's kind of the same thing, right? This CH3, remember, implied hydrogens, carbon at the intersection, that's what that is. Okay, and then over here, last but not least, we have an ether. Right, this ether, what's an ether? Double oxygen. So that's going to be an ether. We have another one right here. This is going to be an alkene. Alkene, okay. And then on this side, it's easy to get this a little bit confused and to think of it as two, but it's really one. And the structure of this, if we really kind of like break it up, it looks like this, right? R group, right? There's a carbon at the end here, a carbon at the end here. You kind of like flip it a little bit. And this is going to be called an anhydride. Okay, and don't get this confused with aldehyde. Aldehyde, I think that's how you pronounce it. Aldehyde is something else. Aldehyde looks like this with an R group. That's what we saw here. Okay, So don't get too confused. All right, there you go. All right, so this is going to be the chunk of the video, resonance structures. I hope starting in the beginning of the video, everything that we've learned previously, you guys got a good understanding of bond line structures, implied hydrogens, implied carbons, formal charge, a little bit of functional group practice. All of that is kind of just to prep us for this curved arrow practice, this resonance. I'm sure you guys also are maybe a little bit familiar with resonance structures from Gen Chem, this idea of moving electrons around. And so if there's any part of the video that you don't really quite understand, I will go back and review that part because it's really important to just not brush over anything. If you don't understand it, really go back and you can put another comment down and I can try to explain it, or go back and just rewatch the section of the video or do your own research before you start practicing with this. So hopefully everything else made sense. And let's do a couple of these practice problems with resonance structures. So resonance structures, it's this idea that electrons are being moved around. So you see these curved arrows, right here. And it's basically saying that these electrons are moving so fast that they've almost exist in two places at once. That's kind of how I was taught. Now, obviously, that's not what's really happening. It's just moving really fast. There's different forms. Some forms are better than the other, right? There's priorities, which we'll go into later. But as far as right now, I want to just kind of recap and remind you guys that every bond line is equivalent to 2 electrons. Every bond line we call what? A sigma bond. But if we have a double bond, right? There's one sigma bond, right? Because there's one bond. But then we have this other bond. Now, we don't call this double sigma bond or duo sigma bond or anything. We say, okay, this is a sigma bond. This is all, by the way, this is a double bond right here. I just kind of spaced it out so I can write what they're called. And this second part is a pi bond. Okay. So now in a double bond, we have one sigma bond and one pi bond. It is really crucial, at least for this step with O-Chem, you cannot move sigma bonds around, because if you move the sigma bonds around, you are changing the entire shape of the molecule, therefore changing the molecule entirety. The sigma bonds are very, very crucial. You can't move those. But you can move these double bonds, this pi bond right here. You can move this pi bond, not the sigma bond. Let me just write. So this pi bond, okay. Sigma bond, no. Do not move the sigma bonds around. And remember that electrons can be converted into a bond, into a pi bond. So for example, if you have something like, actually, we'll do a lot of practice on it. I just want you guys to kind of see that first. Okay, so this problem right here, right? Before you do resonance, I would still draw my hydrogens in, because it's really easy to mess up your hydrogens, where your bonds go. Because at the same time, you don't want to exceed octet on anything. So let's just draw in hydrogens. Just 1, 2, 3, 4, 5, 6, 7, 8. 2 hydrogens. There's 2 hydrogens here. 1 hydrogen, sorry. And then this carbon right here has 1, 2, 3, 4, but it's a plus charge. Right? It has a plus 1 formal charge. So what does that mean? That means there has to be 3. That's 1, 2. So this has to only have 1 hydrogen. And then, of course, this carbon has 3. Okay? And so what we're going to see now is this double bond, this pi bond, is getting moved over here. And that's okay to do. We're okay with doing that. Okay, and so what's going to change is it's going to change where the bond is. So it's going to go from being on this left side to this middle side. All right. Now, when I told you guys, make sure you draw in your hydrogens, this is why. We need to make sure that this double bond being moved, it doesn't exceed any octet for these little carbons over here, right? Because this carbon still has the hydrogen. We can't move those. Those are staying, right? There's still 2 hydrogens here. You can't add or move the hydrogens as of yet. You'll see later on. But these hydrogens are here for good. We can't move it around. And so that means whatever we move our double bond, we need to make sure that these intersecting these carbons aren't exceeding octets. So let's go ahead and count. There's this carbon right here. There's 1, 2, 3, 4, 5, 6, 7, 8. So that's happy. 1, 2, 3, 4, 5, 6, 7, 8. This carbon is happy. 1, 2, 3, 4, 5, 6. This carbon doesn't have 8. But if we remember, there is a plus charge. And so this carbon is going to get a plus charge. Because if we remember, 1, 2, 3, 4, 5, 6, this carbon only had 6 electrons. There's certain elements that are okay with not having a full octet. And so it's really important to know with resonance structures that the formal charge, the sum of the formal charge at the beginning needs to equal the sum of the formal charge to the end. So for example, with this guy, we saw that there is a formal charge of plus, and we ended with the formal charge of plus, right? The only thing that happened is there was just a rearrangement. We just rearranged this double bond, this pi bond, and we moved it here. And by us moving it here, we also moved where the positive charge is going to be. Now, for example, if you see a plus and minus, like let's just say, hypothetically, that the plus still existed here, but there was also a minus. That means that there needs to be a minus on this side, or the sum of these needs to be 0. So plus 1, minus 1, we add those together, that's going to be 0 formal charge. That means whatever happens here has to also have a sum of the formal charges to be 0. They have to be the same from the start to the end. All right, so just keep that in mind. So a couple of house rules. We'll do another problem. Let's do, this is a double. We're moving 2 things at once here, which is okay to do. So remember, there's a -1 formal charge. Overall, the sum of everything is -1. There's no other formal charges. So there's just, this whole thing is -1. So that means at the end of the day, we need to end with a formal charge of -1 here as well on this side. Remember, like I said, the only things that we can move around with resonance are pi bonds right here. We can either move them and convert them to lone pairs because every bond has a lone pair, or we can convert lone pairs to pi bonds. And so that's exactly what we're doing here. We're moving this pi bond and we're putting it on a lone pair here. And we're moving these lone pairs and we're making it into a pi bond. So what that's going to look like on this side is now instead of a double bond, a pi bond existing here, it's going to exist as a lone pair. And instead of there being lone pairs here, we're moving this lone pair and making it into a double bond. And so now we need to go back. We need to make sure that everything is octet, or everything is starting to be like, everything is stable is the word I was looking for. So there's 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So we know there needs to be 2 hydrogens on this carbon. This carbon has, we need 1 more hydrogen. 2, 3, 4, 5, 6, 7, 8. Good. And this has 8 already. And so by us moving this lone pair, right, there's already 2 implied hydrogens. But we also added a lone pair. And where did we get the lone pair? Remember, we're moving the lone pair here. Right? We're moving it out from a pi bond and we're converting it to a lone pair. So does this carbon have 8 electrons, right? There's 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. And what does that mean? What does it mean for this carbon? That means it's stable. It has octet and from the hydrogens and from the lone pair. So it's happy. This carbon has 1 hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. So that's happy. This carbon is good. Now how about this oxygen? 1, 2, 3, 4, 5, 6, 7, 8. So everything is happy. Everyone has 8 valence electrons. Now where's the charge, right? I mentioned that whatever charge we start out, we need to end with. So when we move bonds and we start off with charges, there's also going to be a rearrangement of not only the electrons itself, but the charge as well. And when we're looking at something like this, well, we obviously know there's not going to be a charge on oxygen anymore because we're moving electrons. Electrons hold this negative charge. If we're moving it as a pi bond, it kind of negates that. And we can even see it just by practice, right? We know oxygen from our periodic table has 6 valence electrons. Lines plus dots, there's 1, 2, 3, 4, 5, 6. So that means this is going to be neutral now. This guy's going to be neutral. But for this carbon over here, this carbon is fine because we didn't really switch anything. All we did was rearrange the pi bonds. We're going to calculate the formal charge of this carbon. So this carbon has how many valence electrons? It's going to have 4. All carbons have 4. And so now we see that there's lines plus dots. 1, 2, 3, 4, 5. That's going to be -1. So that's where that formal charge went. It shifted from the oxygen over to the carbon, and that's what the answer is going to be. So at the end of the day, without all of these scribble lines and everything, your answer is going to look like this. Okay? We don't add the assumed hydrogens or anything. We just keep it like that. It's important to make sure you add, 1, the formal charges, right? They're not assumed. You need to add them. You might get docked off points. I'm not sure how lenient your teachers will be. I know mine will. So I would add them, definitely. Add the lone pairs, right, that you converted from this pi bond to a lone pair. Add that. And also make sure you add where the double bond is. All right, right here for this guy. We're moving, I'm going to try to go a little bit faster now. We're moving this pi bond, these electrons over here. So what is that going to look like now? Instead of the bond being here, it's going to be over here. We're literally moving the electrons where the arrow is pointing. And that means that we're going to have a rearrangement of what else? The positive charge. The positive charge is going to go from being here to here. Now, if that's a little confusing, we'll go over that right now. There's on this central, in this carbon, right? There's a carbon here. This carbon has 1, 2, 3, 4, 5, 6, 7, 8, 2 hydrogens. Okay. This carbon has carbon here. 1, 2, 3, 4. Remember, we need to end up with +1. So there's 4 minus 3 would be +1. Would be 1. We'll just say 1. That means there's 2 hydrogens here. Okay. And we're okay with this +1. So if there's 2 hydrogens here, right, and then there's 3 lines, so that's going to be +1. We're happy there. And now that we moved this bond, remember, we're moving this pi bond over here. We have 1, 2, 3, 4, 5, 6, 7, 8. So this carbon is happy, but it also has 1, 2, 3, 4 lines plus dots, which is 0. So this carbon right here is going to be neutral charge. Now, this carbon, on the other hand, there's still hydrogens here. We're not moving the hydrogens. We're only moving this bond. And that means that it's going to have a formal charge now because carbon has 4 valence electrons. This carbon right here. It has 1, 2, 3 lines plus dots, which is going to be 1. And that's where you see the +1. Oh, I'm sorry, guys. 4 valence electrons minus the 3 lines plus dots, 1. I was covering it up. But that's how you see where the shift is occurring. Now let's go to something that's a little bit harder, or looks a little more complicated like this. Now for this guy, what do we have as a formal charge here, guys? What is the sum of all of the formal charges? Well, there are no formal charges, so that means everything here is 0. The total sum of the formal charges is 0. And the reason we know it's 0 is because 1, there's no formal charges, and 2, because there's none, we assume that it's a neutral compound. It's neutral, no charge. And so what are we doing here? We're moving this lone pair, or sorry, this pi bond, we're moving it here. And then we're moving this lone pair over here. Now, you're probably wondering, okay, why do we need to move if we're moving this lone pair, right? Now, we moved it over here. Why do we also need to move this guy? And that's what I was talking about with octet, right? Because if we move this lone pair, right? It's a little noisy outside. There we go. If we move this lone or this double bond and put it over here on this central carbon, how many valence electrons is this carbon going to have? It's going to have 1, 2, or electrons is it going to have sharing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Because of this guy. So that means we need to move this guy to make sure that carbon only has 8. We're exceeding octet. We can't do that. So that's why this double bond is also getting moved up to oxygen, right? And if we do that, right, it already has 2. We're moving it as another 2 so we can get rid of it. Now, the other question we need to ask ourselves is, because we move this lone pair up, is it exceeding octet for oxygen? 1, 2, 3, 4, 5, 6, 7, 8. It's not, right? So that's why we have a double movement, because if we move this guy, right, over here, and we still had our double bond, carbon is not going to be happy. There's way too many electrons around this. It's not, you can't be doing that. Because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that's why we need to move it up. Now, by moving these electrons around, we created some formal charges, right? We already know that there's a hydrogen here. And if we look back on this oxygen, what's the formal charge or valence electrons for oxygen? It's 6. 6 minus lines plus dots. 1, 2, 3, 4, 5, 6, 7. It's going to be -1 formal charge. So this carbon is a -1 formal charge. Sorry, oxygen. This carbon is oxygen is in -1 formal charge. Now for this carbon over here, right? Originally, because it had the hydrogen, 4 minus lines plus dots, 1, 2, 3, 4, it was happy, it was neutral. But now, there's still a hydrogen here, but now there's no double bond here, right, for this carbon. And so that's going to be 4 minus lines plus dots, 1, 2, 3. So now it's a +1 charge. So this carbon is going to be a +1 charge. Oh, there we go. Okay, now you're asking me, hey, well, now that we have this, we know that, I'll erase this for clarity. Now that we know that the lone pairs are going up on oxygen, which is what the arrows indicate, and we know that the pi bond is getting moved over here, which is what we drew, and we also indicated the lone pairs on oxygen, so we added everything. There's still formal charges. You told me, Parso, that formal charges on the left and the right, they need to be the same from start and beginning. And they are, right? Because the sum of the formal charges here is 0. And the sum of the formal charges here, right? +1, -1, they cancel each other out. It's also 0. So this is okay. All right, amazing. We'll do one more on this page. Okay, so this is the same concept as the other one, right? We're moving some lone pairs over here to make a double bond, right? And by doing that, we're going to lose some lone pairs because we're losing it to this pi bond. But now that we've added this pi bond, we also need to move this pi bond over to oxygen because we don't want nitrogen to exceed octet, right? Because if we have this double bond here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's still 10. So we got to get rid of this guy. We got to get rid of this guy. We got to throw it over to oxygen. So now oxygen has its original 4 plus the thing that we moved, the pi bond, and it's going to be 2 lone pairs, right? Remember, 1 bond is 2 electrons. And so now we go back and we make sure that the formal charges still work. They all add up. And the sum of the formal charges here, is what? You got a plus and a minus, so it's going to be overall zero, neutral. And this oxygen, you can just do it really quickly in your head. 6 valence electrons, minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7, minus formal charge. -1 formal charge. And then oxygen, right here, 6 minus 1, 2, 3, 4, 5, 6. So that's neutral. Nitrogen has, I think it has 4 or 5. I think it's 5. Yeah, 5. Right? On the periodic table. If you don't know, just look at the periodic table. It has 5 valence electrons. So 5 minus 1, 2, 3, 4. So this is still a plus charge. Okay? And those sum up to 0. So there's your answer. Beautiful. Now, we're going to draw in the curved arrows. So in the problems before, the curved arrows, these arrows that are indicating where the electrons are moving, were drawn for you. But now we're going to need to draw them ourselves. So if we have a start and an end, right, we're going to draw how are we moving this positive or this negative formal charge? How are we moving this bond? So we need to draw that. And it's as easy as doing this. There you go. You're done. That's the answer. Next problem. And by the way, we're moving it based off the same logic as all the problems we did up here. Same logic. Okay, for this guy, right, we have lone pairs. If I were you, if you have a hard time visualizing everything, I would draw in all the carbons, draw the hydrogens, draw the lone pairs for sure. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And so what's going on here is we're moving this pi bond, right? Because if you look up here, there's no pi bond, right? And this is ending with the -1 formal charge. What's the formal charge of this? Right now it has oxygen has 6 valence electrons. It has 1, 2, 3, 4, 5, 6. So 6 minus 6, 0. So we need to move this. And be precise with your curved arrows. We need to move this double bond. We know there's no double bond here. And we know because there's no double bond, it ends with the -1 formal charge. We need to move this pi bond as lone pairs. Okay, so now it's going to have 1, 2, 3, 4, 5, 6, right? So 6 valence electrons minus lines plus dots. 1, 2, 3, 4, 5, 6, 7. So we're right. There's 6 minus 7 is -1. And now if we see here carefully, we also see there's a double bond here. And we see there's a lone pair on nitrogen. So we're going to go ahead and move that lone pair and convert it into a pi bond. And that's where you're going to get that double bond here. You're getting this double bond from the lone pairs of the nitrogen. All right, beautiful. Okay, now let's do something a little harder. Something like this. I don't know if it's harder and maybe a little bit longer would be the right wording. Now for things like this, I would 100% add all my hydrogens to make sure that we're not exceeding octet on anything, because it's really easy to mess that up if you don't if you don't have all the hydrogens shown. So let's go ahead and add all the hydrogens in lone pairs. Go ahead and do that yourself. Okay. And the way to do these is you see where you're starting from and where you're ending. We're ending here, right? Obviously there's more, but this is the first part. And so we see, the first thing I kind of look for is, are any of the double bonds moving? Where are the pi bonds going? So in this ring, all the pi bonds are remaining the same, right? They're still here, same places. Now, if I look here on this oxygen, I'm seeing that, hey, there's not a double bond here anymore. And my question is, okay, if there's not a double bond, where is it getting moved to? And the way I can tell by where it's getting moved to is from the formal charges. Remember, electrons have, what, a negative charge to it. And so if we're going from a neutral to a more negative state, that means that I know that this pi bond is getting moved up here. Okay? And it's going to give me some more electrons. And that's the first step. So just this little curved arrow. And now I'm going to go ahead and erase this just for clarity for you guys. We know that there is, there's a carbon right here, right? We understand that there's a -1 formal charge here. Now, why is there a plus formal charge on this carbon? If we go back to this carbon, carbon has 4 valence electrons, minus lines plus dots, 1, 2, 3, 4, right? That's going to be 0. But now on here, there's still 4 valence electrons. But we're moving this double bond that was here, that was incorporated in this 4, and now there's only 3, 1, 2, 3. So that's why we have a +1 formal charge right there, okay? So that's the curved arrow for that guy. Make sure for these, you draw in your electrons, your lone pairs. Okay, now second step. Where are the lone pairs getting moved to? Okay, are we seeing any change in lone pairs? Well, if we look, the oxygen stays the same, right? Everything is the same. The only thing that's different is the movement of this pi bond going here, causing a causing a positive causing a +1 forward charge. Sorry about that. And so we're quick to understand, okay, that means we're moving this pi bond. We're going to be moving it here, right? And because we're moving electrons away from this carbon, it's going to have a positive charge. I don't want to keep doing formal charge, like writing it out. I don't want to waste your guys' time. I will just this last time. I hope you guys have enough practice with it. But basically the idea is there is 1, 2, 3, 4, 5, 6. So there's a hydrogen here, right? 4 valence electrons for carbon. Minus 1, 2, 3, 4, which is 0 formal charge. But for this guy, we still have the hydrogen here. Still 4 valence electrons. 1, 2, 3. That's that +1 formal charge, okay? So we're indicating that the lone pair goes here. Now, let's see what we're working with. We still want to add our lone pairs here. We're seeing that this double bond is getting moved. We're moving it here, and the electron, the positive formal charge, is going to be on this carbon now. So we're just going to draw an arrow over here. Last but not least, oxygen is the same. Double bond here is the same. Double bond here is the same. Double bond here is different, right? It used to be here, but now it's here. And the positive charge used to be here. Sorry, it used to be here. Now it's here. So we're going to draw a curved arrow over there. Formal charge logic remains the same. Now, every time I did formal charge, remember I drew in these hydrogens because the implied hydrogens matter, right? If I didn't include this hydrogen, this would have been a +1 charge. Because think about it. If we didn't include that 1, 2, 3 lines plus dots, that would have been 3. We have to include the hydrogens. Be careful because those hydrogens can blend in, camouflage in. It's like so easy to miss and to not add in. So that's why for me, if you're dealing with resonance in the beginning, draw in your hydrogens. Make sure you're not exceeding octet. Make sure you're getting your formal charges right. All right. So now we are starting to do a little bit harder problems. These problems are, now you don't have a start and a beginning. You have to just kind of assume where the electrons move, where the formal charges move, based on the rules that you have, based on what you're allowed to do. And that's not too bad. Once you get a lot of practice with these guys, it's really easy to, and these guys as well, it gets a lot easier to kind of just become second nature almost. So right off the bat, I'm seeing a couple of things we can do. If we remember from the previous problems that we just did, we can move around electrons here. We can have oxygen have a negative formal charge, and that's exactly what we'll do. So we're going to move this lone pair, right? We're going to move it over here. And make sure when you guys are moving lone pairs and pi bonds, it's moving it to the neighboring thing, moving it to the neighboring element. Like for example here, like let's just ignore everything else, right? Let's keep in mind this bond. every time we've moved a bond here, like in this ring, we always moved it to its neighbor, right? We moved it here, we can move it to this carbon, or we can move it over here, but we can't move this pi bond all the way over here. We can't move this lone pair all the way over here, right? It has to be like right next to each other. They have to be neighboring. Same, you know what I mean? I hope that makes a little bit more sense. So we're going to want to move this lone pair neighboring. And now we're going to have this double bond, right? Ignore the lone pair. Imagine that it's a pi bond now. If we look at nitrogen, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's way too many electrons. So we're going to need to kick this guy out. We're going to need to boot that guy over to the oxygen, and that is going to have a lone pair itself. And so that's how you're going to draw your curved arrows. And your answer is going to look like this. This is going to be the new compound right here. The resonance structure of it. Okay. This nitrogen is still going to have a plus charge. Oh. Right? We've moved the electrons here as a pi bond, which we're representing here. And we moved the pi bond up here and added as another lone pair, which we're representing here. We didn't really change anything to the formal charge, because if you look at it, the only thing for nitrogen is we've moved this pi bond, and instead of it being connected to this oxygen, it's just connected to this oxygen. So its formal charge is going to remain the same. But now for this oxygen, this is going to become neutral. So this is going to be 0, right? And this is going to become -1. So calculate your formal charges for each of these. And the sum of the formal charges, +1 - 1 is 0, +1 - 1, +1 - 1, 0. So we know we're right there. All right, now let's do something like this. This one, let me see. I think this one, there's a couple steps. There's basically what we're going to be doing is we're going to be recreating this problem, all this, except there's not going to be a start ending. It's not going to show us the steps. We have to do it ourselves. So first thing I like to do, and I'm really thankful I don't have to draw it out on paper, because writing everything out like multiple times is a little monotonous, but it's fine. Okay, I'm just going to go ahead and duplicate this for later on. Actually, I'll duplicate it at the end. All right, so what are some changes we can make when I'm first looking at this? Well, we have a lone pair on nitrogen, right? So we can do something with that. We can't add the lone pair to carbon, because you can't really move the electrons around carbon. This already has octet, right? There's 8 bonds. There's 4 bonds already. There's 1 here, and there's 3 on the hydrogen, and each bond has 2, so that already has 8, so 4 times 2. Same thing here. But we can move around this guy. We can move stuff here in this section. So we're going to go ahead and move these lone pairs. We're going to move it down here, right to this neighboring. And we're going to boot this guy, because if you think about it, now if we have this imaginary pi bond that we're creating, this carbon is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can't have that. And so we're going to move this lone pair, and we're going to add it to this carbon as a lone. We're going to move the pi bond as a lone pair, so we don't exceed octet on this carbon. And what that's going to look like is we're going to have a double bond right here, and we're going to have a lone pair right here. And by doing that, remember, there's no formal charge, it's neutral. And so we know that nitrogen is going to be +1 charge, because valence electrons is what? 5 minus 4 is 1. This carbon is going to have a -1 charge, and that's going to be sum of 0. Still the same. Now, there's a couple more things we could do. I'm going to go ahead and this is where having an iPad becomes really, really handy. There we go. Okay. Now there's some more stuff we can do. If we see here, we still have a lone pair that we can kind of work with. And we can still boot all of these guys and move them around. So we're going to do just that. We're going to move, let me make my curved arrows another color. We're going to move this lone pair. We're going to add it here as a pi bond. But now remember, there's implied hydrogens on this carbon. And so by us moving the lone pair, it's affecting two carbons now. Because originally this lone pair is only affecting this singular carbon right here. But by moving it as a pi bond, we're affecting this carbon. And that's going to exceed octet for this guy since there's a double bond here. So we're going to need to kick this guy out. And we're going to need to add it as a lone pair here. Same thing we did over here, guys. And so when we're going to redraw this, I guess the curved arrow should be on this step right here. When we redraw this, it's going to look a little different. It's going to look like this. All right, we're moving those lone pairs as a pi bond, and we're kicking this pi bond out, and we're moving it as a lone pair. And so now this plus charge is still here, but now the minus charge is getting moved here. Still formal charge of 0, neutral, so we're happy. And we're just going to quite literally continue this a couple of times. I'll make this smaller so we have more space. Copy this. Okay. Like again, we can move the lone pair. Move it right here. This is going to exceed octet, this carbon. So we're going to kick this carbon, boot it up here. I keep driving on the wrong step. Move it here. These lone pairs. Move this pi bond to this carbon. So what that's going to look like now. Oh. We're going to have a double bond right here. And we're going to have lone pairs -1 charge here. All right, last step, one more step before there's no other resonance structures that we could draw. Okay. We can move this lone pair, same thing as we did before. We can move it here. But if we do that, that means we need to boot this lone pair, because remember, if we add our lone pair as a pi bond right here, it's going to be affecting this carbon and this carbon. This carbon already has a double bond. This nitrogen has a plus formal charge. So that means it's okay if it takes some more electrons. So we're going to boot it and we're going to give it to nitrogen, kind of at the starting point. Nitrogen is going to end up back with 2 lone pairs with a neutral formal charge. And so now it's going to look like this. Right? We're moving the lone pairs. We're moving it as a pi bond over here. Okay? And then we're moving the lone pair here. We're moving it to the nitrogen. And there you go. Now, it looks the same, the start and the end, right? Except if you look at the double bonds, they're shifted slightly. So there used to be a bond here, but now we're shifting it here. All right, guys. So that's that resonance problem. We can do a couple more resonance problems. Actually, I don't think we can. I'm going to do 2 more. Almost done. 2 more. Stick through it. 2 more, and then you'll be masters by then. All right, 19. Okay, so we're going to do problem set B. Let's do B. All right, so looking at this problem, what are some things that we already know? We can move 2 things. What can we move? We can move lone pairs. We can move what? Pi bonds. So we're going to go ahead and move this pi bond here, and we're going to move this lone pair, and we're going to move it to over here on its neighboring. And so that's going to look like this now. Remember, we're moving the pi bond and moving it as lone pairs. We're converting it. And we also are going to have a double bond right here. Okay. So there's no more pi bond here. There used to be, but we moved it. And there used to be a single bond, but now there's a double bond because we've moved the lone pairs and created a pi bond. Remember, single bond is just this. That's a sigma bond. Pi bond, this is all a double bond. This thing is a double bond, but this half is a pi bond. Just as a recap, if you're confused about when I say moving pi bonds. This is a sigma bond. This is a pi bond. It doesn't matter. This could be the pi bond. This could be the sigma bond. Basically, the point is that one of the bonds in the double bonds is a pi, the other is a sigma. And the one you can move around is the pi. So that's why we're allowed to move this. And there's your resonance structure. But we need to add the formal charges, right? We started off with 0. We need to end with 0. So there's a -1 formal charge here. And there's a +1 formal charge here. Let's do the quick method real quick. 6 valence electrons, minus lines plus dots. 1, 2, 3, 4, 5, 6, 7. 6 minus 7, 1. Nitrogen has 5 valence electrons. So it's going to have, in lines plus dots, 1, 2, 3, 4. There's no dots. So 5 minus 4, 1. +1. All right, let's do this guy. So for this guy, what can we do here? This is a carbon, right? We know that there's a hydrogen here. If we have 4 valence electrons, we need 5 to meet -1, right? So that's going to have 1, 2, 1, 2, 3, 4, 5. Right? There's 2 implied hydrogens, and there's 2 lone pairs. Now you may be asking me, how did I figure that out? Well, okay, I know this carbon right here has a -1 formal charge. It's indicated right here. In my head, I wrote it out here for you guys. 4 is the number of valence electrons carbon has. So in order to get to -1, we need to have 5 lines plus dots, right? Which is how we've been practicing it. So if I know that, that means 1, 2, 3, 4, 5 is what we need to add. This has to fulfill octet. 1, 2, 3, 4, 5, 6, 7, 8. It fills octet. We're all good. Lines plus dots show that it's a formal charge of -1. So that's how I know that. Now we can move this lone pair over here, and we can add it over here and make a double bond on this side. But by doing that, we're going to exceed octet for this carbon here. So we're going to need to move this carbon. We're going to need to move this double bond, this pi bond, and have it as a lone pair. And so we're going to convert that into something that looks like this. Don't forget, we're moving the lone pairs here, and there's going to be a minus formal charge on this carbon. And so that's what that's going to look like. Okay. Now, there are a couple things about resonance that I think is review for you guys in Gen Chem, I believe, maybe. But there are rules to resonance structures about what's more favored. So those are the less amount of formal charges you have, the better. You want to make sure that the formal charge, like for example, if there's a minus or a plus, it's the minus or plus, like for example, if you have a formal charge of -1, which we have here, you want to make sure that the -1 is on the most electronegative element. All right? There's something called an electronegativity chart. You can look it up. And basically, it's just a numerical value that shows the difference in electronegativity between certain elements, And when you're doing resonance structure, there's going to be multiple, right? We've drawn a lot here. We drew like 4 of them here. And out of all of these, there's the best resonance structure that it's most likely going to be in, right? The best resonance structure is kind of what we say. And so the rules are 1, formal charge on respective element. Now, what does that mean? If you have a formal charge on carbon, which is -1, right, versus oxygen, which is going to be better? Which is more likely going to occur? If you go and look up electronegativity chart right now, if you go on it, oxygen has a higher electronegativity. So that means the structure that has oxygen and there's a formal charge of -1 on oxygen is going to be preferred. It's going to be better than carbon because electronegativity value for carbon is lower than oxygen. So that's what that means. But if we had, right, it's a little different there. So that's why I said formal charge on respective element. 2, least amount of formal charges. Least. Okay. Like for example, if we have compound A versus compound B, and this is plus formal charge minus formal charge, and this has 2 plus 2 minus 2. Yes, both of them, the sum of the formal charges of these compounds is 0, but there's a less amount of formal charges. It's only 1 compared to 2. It's only +1 -1 compared to +2 -2. So that's what that means. And there's some other ones as well. You can look at it. I think there's like 4 or 5. The other one is they need to be like the one where the formal charges are closer together is the better one as well. All right, so now let's understand why this guy is more stable. Why is this molecule, A, we'll say A, more stable than B? And the reason for that is because of resonance structure. So if you have anything that shows that has resonance structure, that means it can move the electrons around. And by moving electrons around, it's more stable, it's happy. It gives this electrons to everyone, so no one's really in this hyper unstable state. And so remember, we're going to have lone pairs here. We can move this lone pair here, make a double bond, and move the pi bond and move it here as lone pairs. For B, you can't do that, right? There's no oxygen. There's a carbon here. You can't move any more. You can't really move electrons to carbon like that. So that's why A is going to be more stable because it can participate in resonance structure, right? And it's going to end up with oxygen having a formal charge of -1 versus carbon having a formal charge of -1. Because you can still do the same thing. All right, and this is just considerably more stable, having the formal charge on oxygen being -1 versus carbon, because like I mentioned, oxygen has the more electronegativity, has more electronegativity. Now again, for this, why is B more stable than A? Now, if we look at this, these are all sigma bonds, right? There's lone pairs here, but that means we can't move anything and you can't move anything out because we're going to cause a problem with octet. But for B, that's not applicable. We can move stuff around. We can move this lone pair here, but hey, parts of the octet is messed up for this carbon. Well, that's fine. We'll just move the lone pair here. You can't do that here, right? That's not possible. Now, if you're still curious on why that is, go back and draw your hydrogens, right? I'll only draw the hydrogens for this section because we're not really dealing with the other sections. This has 1, 2, 3, 4, 5, 6, 1 hydrogen here. This hydrogen has 1, 2, 3, 4, 5, 6, 7, 8, this carbon. So there's no hydrogens on this carbon, okay? Now this oxygen has a formal charge of -1, so 1, 2, 3, 4, 5, 6. 6 minus 7 minus the dots, right? If we move this lone pair here, let's go ahead and do that. Let's imagine we did that, right? Look at this carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, including this hydrogen. Right? There's too many electrons, and there's nothing we can do about it. We can't move sigma bonds around. Otherwise, we're breaking this ring. We can't move this guy here. So that's done. So basically, this compound is going to stay like this. You can't have any resonance. But on this guy, you can, right? There's still the same number of lone pairs. If we move this guy here, right, it has a double bond here. So we'll go ahead and do that. This carbon is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? It's exceeding octet. But we can move this double bond here. And that would be same carbon. 1, 2, 3, 4, 5, 6, 7, 8. So it's happy. It's fine. Sorry. It's fine. So now you can kind of see why this B is more stable than A. It can participate in resonance. It can move its electrons around, share it between these resonance forms. And so same thing with here again, guys. Why is this the major contributor? It's because where's the electronegativity? Where's the formal charge? There's formal charge on oxygen compared to formal charge on carbon. Okay, and so as we know, we want to make sure the formal charge is on its respective electronegative element. And so oxygen has a higher electronegativity versus carbon. Now, this guy right here. You may be wondering, why is this the more major contributor? And the reason for that is because octet is filled, right? And there's the least amount of formal charges. There's no +1 or 0 or -1 formal charge like shown here. Not only does it fulfill octet, there's no formal charges on this guy compared to this guy. So this is why the major contributor is going to be here. And we don't draw this resonance form because this is much better. This resonance form is much better. This has formal charges. This does not. And so the charge separation, these are two identical things, right? It's a carbon and a carbon. We don't really want to do that. So this is the only contributor. We don't draw it like this. And so for this guy down here, it's basically asking why is this one, the following hydrocarbons, blah, 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 explain why OCH3, this guy, is more stable than this guy. So basically what it's saying is this is good, this is bad. Now I want you to take a second and really think through this. Where's the positive charge right now? It's on carbon, okay? The next question you need to ask yourself is, okay, well, if there is a +1 and it's on the same electronegative, it's on the same element, that means you can't really compare electronegativity because it's on the same element. So what do we do next? We know that there's lone pairs here. That means we can have resonance here, guys. We can move this double bond and we can have it be a double bond, right? Okay, we can have a double bond, and this would be the plus charge. It would still have the same charge, but there's resonance involved. And so when there's resonance involved, it's more stabilized. And so this is why this is going to be the better one. Well, that's the end of it, guys. I know this was a long video. I truly hope that it helped. We covered a lot in this video. We covered, basics. We covered bond line structures, resonance, formal charge, functional groups. So there's like 6 or 7 things incorporated in this video. I would recommend, at least for me, what I would do would be to find specific YouTube videos, like 5-minute ones maybe, on the specifics parts, like find one for resonance and then go and find one for functional groups. And then come back to me and let's just do practice problems together. That's what I do. Because a lot of the times, like I mentioned, I would go out and I would do the problems, learn how to do it. And then on my homeworks, there was just problems that were never on YouTube videos that I found that were helpful. It's just the difficulty level of those problems were nothing compared to my test quizzes and homeworks. But we did a lot of the harder problems on this. There were some hard problems on here. And there were some easier ones as well. But I hope you guys understood what we went through today. Keep doing practice problems. If you guys have any other questions, just go ahead and leave them down. I appreciate it. I'm going to be having a couple other videos on just like the first year of O-Chem. So there's going to be a series coming out. And we'll go in through it later. So as you go in through your course, or if you're reviewing, I'm going to be dropping videos on different topics as well. So I hope you guys learned a lot and enjoyed it. But keep doing those practice problems, and I'll see you in the next one.